Hello everyone. Today in this session I am going to discuss about isomerism in coordination compounds. Isomerism in coordination compound. So first we have to know about what is isomerism. So what is isomerism? So what is the phenomenon isomerism? So the complexes which contains same chemical formula, same chemical formula but different physical and chemical properties due to its different structural arrangements. Those are called isomers and the phenomenon is called isomerism. Okay, I repeat it again. So what is isomerism? The compounds which contains same chemical formula but different physical and chemical properties due to its different structural arrangements. So those compounds are called isomers and the phenomenon is called isomerism, right? Now we have different types of isomerism, mainly structural isomerism, and second one is stereoisomerism. Okay, so in this session, in this video, I am stick to structural isomerism. So what is structural isomerism? So difference in structural arrangements. So that you know what is isomerism? Different in same molecular formula, but difference in structural arrangements, right? So this structural arrangements we have different types of isomerisms. And the main first one is ionization isomerism. So ionization isomerism. So complexes which contains same molecular formula but they forming different ions in the solution. So those isomerisms called ionization isomerism, and those compounds are called isomers, ionization isomers, and the phenomenon is called ionization isomerism, right? Okay, what is ionization isomerism? The complexes which having same molecular formula but they forming different ions in the solution. Let's understand better with the help of example. Let's take CONH3 5 times SO4 Br and CONH3 5 times Br SO4. Okay, so these two compounds have same chemical form, same molecular formula. That is, you are having cobalt, 5 ammonia molecules, 1 sulfate, 1 bromide. But the difference is when this complex is dissolved in aqueous solution. There are two types of ions. One is cation, and the other one is anion. So what are those ions? The CONH3 5 times SO4 plus and Br minus. That means when this complex is dissolved in aqueous solution, which gives Br minus ion, which gives anion Br minus in the aqueous solution. So when this complex is dissolved in aqueous solution, which gives CONH3 5 times Br 2 plus and SO4 2 minus. Okay. So when this complex dissolved in aqueous solution, which gives CONH3 5 times Br2 plus and the anion SO4 2 minus. Okay, so both these compounds have same molecular formula, but they forming different ions in the aqueous solution. Okay, so these two compounds are ionization isomers. These two complexes are ionization isomer. In one of the isomerism that is called ionization isomerism. Right? Let's take another example. So first example. Let's take second example. Platinum PtNH3 thrice NO2 and Br. Okay, and next PtNH3 thrice Br NO2. So these two are ionization isomers. Okay, so why here? So in this complex dissolved in aqueous solution, which gives PtNH3 thrice NO2 plus Br minus. That means this complex which gives Br minus anion in the aqueous solution. This complex which gives NO2 minus ion in the aqueous solution, right? So these two ions are these two complexes are ionization isomers, right? So this is about ionization isomerism, okay? Right. So what is ionization isomerism? So the complexes which having same molecular formula but they forming different ions. So you are having cobalt, 5 ammonia molecules, 1 sulfate, 1 bromide, but they are forming different ions in the aqueous solution. You know, this part will ionize, this part will not get ionized because this is present in coordination sphere. Okay. Right. So the second isomerism is hydration isomerism. Second one is hydration isomerism, right? So hydration, this is a special type of ionization isomerism. So in ionization isomerism, the anions both are negative ions. So negative ions are interchanging between coordination sphere and ionization sphere. In ionization isomerism, the anions are interchanging between coordination sphere and between coordination sphere and ionization sphere. So here the new solvent molecule, here the solvent molecule will interchange with the anionic ligand, the interchanging with the negative ions, right? For example, taking example Cr NH3 5 times. Sorry, Cr H2O 6 times Cl3, right? Okay. So Cr H2O 6 times Cl3. So this is one complex, and Cr H2O 5 times Cl2 H2O. So what I am done here? So what I did here? So here one chlorine is replaced by one water. So one of the H2O molecule H2O is replaced with this chlorine. That means here interchanging of solvent molecule and chloride. So that means and taking third CO, this time I am replacing 2 water molecules. So coordination number retains same, here 6, 5 plus 1 6, 4 plus 2 6, right? Cl2H2O. Okay, so these three complexes are hydration isomers. Okay, so by here solvent molecule, that is water molecule, will exchange with the negative, that means negative ligands which are present in, so negative ions which are present in ionization sphere. Okay, for example this complex. So when this complex, so all these three complexes having same molecular formula. So it contains 1 chromium, 6 water molecules and 3 chloride ions. So 1 chromium, 6 water molecules and 3 chloride. Here also 1 chromium, 6 water molecules and 3 chloride. But they having different physical and chemical properties. That is the definition of isomerism. Na? So Cr H2O 6 times Cl3, when this complex is dissolved in aqueous solution, which can be dissociated as CrH2O 6 times 3 plus and 3 Cl minus. CrH2O 6 times 3 plus and 3 Cl minus, right? Okay. That means, for example, I am treating with a concentrated sulfuric acid. So concentrated sulfuric acid, this is dehydrating agent H2SO4. So if the molecule which if any molecule which contains water molecule, this sulfuric acid remove that water molecule. Okay, dehydrating agent. Now adding H2SO4 to this complex, right? So do not lose any water molecule on treatment with sulfuric acid, right? In the next AgNO3. When this complex solution is treating with AgNO3 solution, here 3 Cl minus is 3 Cl minus are available. So these 3 Cl minus are reacting with Ag plus and forming AgCl precipitate. That means number of chloride ions available here to precipitating with Ag plus, that is 3. So 3 chloride ions are reacting with Ag plus and forming AgCl precipitate, right? So these two. Next coming to this complex, second complex, Now here loses one water molecule because one water molecule is out of the coordination sphere. One water molecule is out of the coordination sphere. That means loses one H2O molecule. Loses one water molecule. Okay. And here how many chloride ions are precipitated with Ag plus when reacting with AgNO3? Here 2. By looking this complex here, we are having 3 chloride ions now, but so only 2 chloride ions are out of coordination sphere. Only these 2 chloride ions are ionizable. So this part will ionize. This part will not get ionized. So only these 2 chloride ions are reacting with Ag plus in the solution and forming AgCl precipitate. That means the number of chloride ions are here available 2. So 2 Cl minus are reacting with Ag plus and forming AgCl precipitate. Okay. Next here. So coming to third complex, and this here loses 2 water molecules. Loses 2 water molecules on treatment with concentrated sulfuric acid, because 2 water molecules are out of the coordination sphere. So 4 water molecules in coordination sphere, 2 water molecules are out of the coordination sphere. Only these 2 water molecules are reacting with sulfuric acid and they are removed from this complex. Okay, right. So and how many chloride ions are reacting with Ag plus ions? Only one, because only one chloride ion reacting with Ag plus, because only one chloride ion in ionization sphere. So this part will ionize as Cl. So this complex will ionize as COH2 4 times Cl2 plus and Cl minus. So this Cl minus reacting with the Ag plus and forming AgCl plus. That AgCl precipitate. Right. How many chloride ions are available here? Only one chloride. So loses 2 water molecules and only one Cl minus precipitated as AgCl. Right. So this is about hydration isomerism. So what is hydration isomerism? So hydration isomerism is a special type of ionization isomerism. So in ionization isomerism, the anionic ligand, that means the negative ions are interchanging between the coordination sphere and ionization sphere. Here the solvent molecule is replacing with interchanging with negative ions, right? Like Cl minus, Ob minus, F minus, whatever it is in ionization sphere. So which is replacing with the anion which is present in ionization sphere. The negative ion which is present in ionization sphere, right? So I am taking these three complexes. These 3 complexes are hydration isomers. All these 3 complexes having same molecular formula, same molecular composition, but they are having different chemical properties. Okay, when reacting with sulfuric acid, here do not lose any water molecule, because all these water molecules in coordination sphere, they cannot they ionize. So they are not reacting with sulfuric acid. But here when reacting with sulfuric acid, here one water molecule is out of coordination sphere. So this water molecule will get removed. So it loses one water molecule on treatment with sulfuric acid, right? So here loses 2 water molecules on treating with sulfuric acid. So in the same way, when treating with AgNO3, these 3 chloride ions are precipitated, and when treating with this AgNO3, this complex here 2 chloride ions are precipitated, here 1 chloride ion is precipitated. Okay, because these chloride which is in coordination sphere will not get ionized, which is not available as Cl minus. That's why it is not reacting with the Ag plus, right? And the next isomerism, third isomerism, that is linkage isomerism. Right? Third isomerism, linkage isomerism. So this type of isomer is exhibited of complexes which contains more than 10 ligands having more than one donor site. That means the complexes which contains ambidentate ligands. So what are ambidentate ligands? Ambidentate ligands. Ambidentate ligands, the ligands which contains more than one donor site. For example, taking NO2 minus. Here nitrogen is donor atom, and the same time oxygen also, nitrogen having one lone pair of electron and oxygen also having lone pair of electrons. So both are capable to donate its lone pair of electrons to the central metal atom. So here having 2 donor atoms, but at a time donates 1 lone pair of electron, either nitrogen or oxygen, right? And cyanide. Okay, Cn also, carbon having 1 lone pair of electron, nitrogen also having 1 lone pair of electrons. So both are capable to donate its lone pair of electrons, but at a time it donates only 1 lone pair of electrons to the central metal atom, either carbon or nitrogen. Okay, and Cn minus, Cn minus and NCS minus and NC and ONO. If nitrogen donates this lone pair of electrons, can be written as NO2 minus and called as nitro in the nomenclature. So if oxygen donates this lone pair of electrons, written as ONO, and it can be called as nitrito in the nomenclature. And cyanide, if carbon donates this lone pair of electrons, that is cyano. If nitrogen donates this lone pair of electrons, that is isocyano. If SCN minus, thiocyano. If sulfur donates this lone pair of electrons, can be written as SCN minus and called as thiocyano. If nitrogen donates this lone pair of electrons, and written as NCS minus and called as thioisocyanato in the nomenclature, right? So complexes which contain this type of ligands, this type of amidite ligands are involved in the isomerism, that is linkage isomerism. So those isomers are called linkage isomers, and the phenomenon is called linkage isomerism, right? Let's see an example. CONH3 5 times ONO Cl2, right? And CONH3 5 times NO2 Cl2, right? So these two are linkage isomers, because here ONO written as ONO, that means here oxygen donates this lone pair of electrons to the central atom, that is cobalt. Here NO2 minus, that means nitrogen donates this lone pair of electrons to the central atom. So these two are ambidextrous ligands, both are having same molecular formula, but the linkage, that means here oxygen linkage to the central atom, that means, and nitrogen linkage to the cobalt, right? So this is one example. And second example, if you see the IUPAC nomenclature for this complex, here nitro, NO2 minus can be called as nitrito if oxygen is donor atom. Here nitro in the nomenclature. Here pentaamine, nitrito, cobalt, oxygen state of cobalt here 3, cobalt 3 chloride. Here pentaamine, nitro, here nitrito, here nitro. So nitro, cobalt 3 chloride, right? Next, let's take another example like MnCO5 SCN and MnCO5 NCS. So these two are linkage isomers. Here both are having same molecular formula, both are having same number of ions, and central metal atom is same. But the difference is here sulfur donates its lone pair of electrons to them. That is manganese linked through sulfur here. Here manganese linked through nitrogen. That means so these two are ambidextrous ligands. So this is thiocyanato. This is isothiocyanato. Isothiocyanato. Here sulfur donates its lone pair of electrons to the central atom. Here nitrogen donates its lone pair of electrons to the central atom. Right. So these are the linkage isomers. So you can frame your own examples by changing this ambidextrous ligands. Let's take another example. You can frame another example like CrH2O 5 times Nc, CrH2O 5 times Cn. Okay, right. And the fourth isomerism, the next isomerism, so that is a coordination isomerism. Coordination isomerism. So what is coordination isomerism? So here in this isomers the complexes. So both cation and anion. So both cation and anion both are complexes. So cation and anion both are complexes. That means here we are having two coordination spheres. One coordination sphere is cation, another coordination sphere is anion. Right. So here the ligands are distributed between these coordination spheres. Let's understand with the example. Let's say CONH3 6 times CrCN6. Okay. So here CONH3 5 times, CONH3 6 times 3 plus, because if it is here ammonia is neutral ligand, so the charge over the complex is 3 plus, because here it is 3 minus, so this can be balanced by 3 plus here. CONH3 6 times 3 plus, this is cationic complex. CrCN6 3 minus, this is anionic complex. Now so here ligands are distributed between these coordination spheres. That is CrNH3 6 times CO CN6, right. Now here also CrNH3 6 times 3 plus COCN6 3 minus. So both of these complexes are coordination isomers. So by observing these complexes, right, by looking over this complex, here cobalt is center metal atom, ammonia is ligand. Here chromium is center metal atom, cyanide is ligand. Here over this coordination sphere, here having 3 plus, here we are having 3 minus. Left hand side always you have to write cation, right hand side always you have to write anion. So here 3 plus and here it is 3 minus. This is cation complex and this is anionic complex. Now coming to here, CrNH3 6 times 3 plus. CrNH3 6 times 3 plus COCN6 3 minus. Here chromium complex is the cation complex. Here chromium complex is anionic complex. Okay, that means here ligands ammonia and cyanide are distributed between this and interchanged between these two coordination spheres. So that's why this complex is isomerism is coordination isomerism, right? Let's take another example. Right, CuNH3 4 times PtCl4 2 minus. Okay, so here CuNH3 4 times 2 plus PtCl4 2 minus. So this is your cationic complex, this is your anion complex. Over this complex here we are having 2 plus, over this complex this 2 plus will balance as here 2 minus, right? So this is cation complex and this is anionic complex. And the isomer, the coordination isomer of this complex is Pt and H3, just interchange ligands 4 and CuCl4, right? CuNH3 4 times PtCl4, this is cation complex, this is anion complex, and PtNH3 4 times 2 plus CuCl4 2 minus. Here platinum complex is cation complex, here copper complex is anionic complex. Here copper complex is cation complex, platinum complex is anionic complex. So both are having same molecular formula, same number of cations, same number of copper, same number of ligands, right? Copper and copper, one platinum and another one platinum, and 4 ammonia molecules, here 4 chlorines and here 4. Same molecular formula, but it's a difference in coordination. Here it acts as a cationic complex, here it acts as an anionic complex. Here copper is a cation complex, here copper is an anionic complex. Okay, let's take another example. Let us say COEN thrice. So then diamond again and CrC2O4 thrice. Okay, COEN thrice, CrC2O4. So what is the coordination isomer for this complex? Simply interchange ligands. Cr diamond thrice, CO C2O4 thrice. Okay, so COEN thrice, CrC2O4 thrice. Here this is cation complex, here this is anionic complex. Here it is cation complex, here it is anionic complex, right? So here cobalt. What is the ionic nomenclature for this complex? So tris. Here 3 ethylene diamines now. So tris ethylene diamine cobalt. Here over the cobalt we are having over the coordination here we are having 3 positive and here it is 3 negative. So here bis ethylene diamine cobalt 3 and here tris. So tris ethylene diamine cobalt 3. Here tris oxalate chromium 3. Here chromium also oxygen state, here C2O4 2 minus. Okay, and overall charge is 3 minus 6 minus 3, that is chromium plus 3 oxygen state. So minus 6 plus 3, that is minus 3. So chromium over the coordination sphere you are having minus 3 oxygen state, over the coordination sphere you are having plus 3 oxygen state. Here chromium plus 3 and cobalt plus 3. Cobalt which is in plus 3 oxygen state, here chromium in plus 3 oxygen state. Here also chromium plus 3 oxygen state, cobalt plus 3 oxygen, but the charge over the coordination sphere is different. Here plus 3 coordination sphere, over the coordination sphere you are having plus 3 oxygen state, over this coordination sphere you are having minus 3 oxygen charge, right? So this is coordination isomerism, right? And the next ligand isomerism. Ligand isomerism. So ligand isomerism. So when isomeric ligands associated with the complexes, so those isomers are called ligand isomers and the phenomenon is called ligand isomerism. Let us take an example. CO ethylene NH3 twice PN twice. So here it is oral 3 plus, right? CO NH3 twice, PN twice, 3 plus, and CO NH3 twice, PN twice, right? So these two are also having 3 plus. So these two complexes are ligand isomers. Let's see. So here PN and TN. So cobalt, 2 ammonia molecules. Here also 2 ammonia molecules. Here PN. So what is PN? What is TN? The ligands. So PN. So CH2, CH3, CH2. So ammonia NH2, NH2. Right? So this is 1, 2 diamino, 1, 2 diaminopropane. So 1, 2 diaminopropane, 1, 2 diaminopropane. Here TN. So TN is CH2. So it is binding. So both are binding ligands. TN, PN both are binding ligands. CH2 and NH2. Right? So the position here, 2 ammonia groups, 2 amine groups present in present on 1, 2 positions. Here 2 amine groups present on 1, 3 positions. 1, 2, 3. 1, 3 diaminopropane. Here 1, 2 diamino, 3 carbons na, so prop. So 1, 2 diaminopropane. So these are positional isomers, and here this so TN. So this is CH2. Actually it is methylene. CH2 methylene. So 1, 2, 3. So you are having 3 CH2s na. So trimethylene diamine. So this this ligand, this molecule is also called as trimethylene diamine. So that's why it is TN. Trimethylene diamine. Here it is a diaminopropane. 1, 2 diaminopropane, PN propane. Right? Here trimethylene diamine, that is TN. So these two are binding. This is here and here. So these two are binding ligands. So here isomerism in ligands. That's why it is a ligand isomerism. Okay, right? So this is about ligand isomerism. And isomeric ligands are associated with the complexes. Example, these two complexes. These two complexes are ligand isomers. And the last one, right? The last one, 7th one, sorry, 6th one, polymerization isomerism. So actually polymerization isomerism is not true isomerism, because here complex have different composition, different molecular composition. So polymerization isomerism is not a true isomerism, because the complexes are not same composition. Like let's say an example. So PT NH3 twice Cl2 and PT NH3 4 times and PT Cl4. Two are the polymerization isomers. Let's take another example. CO NH3 thrice NO2 thrice. Right? Now next CO NH3 6 times, CO NO2 6 times. Right? Now here, so by simply looking over these two complexes, they are not isomers, because here 1 platinum, here 2 platinum. They are not same molecular composition, but they have same empirical formula, right? That means the ratio is same. Here 1 platinum, let's see. So 1 platinum and 2 ammonia. and 2 chlorides. Here 2 platinums. So 2 platinums and 4 ammonias and 4 chlorides. So that is 2:4:4, that is 1:2:2. Here also 1:2:2. Okay. In that way, in the second also they have same empirical formula. The molecular composition is different, but they are having same empirical formula, right? CO NH3 thrice, so 1:3:3:3. But here 2:6:6, 2:6:6. That means 1:3:3. Okay. So these two are the polymerization isomers. And the next isomerism is coordination. Seventh one, coordination position isomerism. So what is coordination position isomerism? Here this type of isomerism occurs in the complexes which are having bridging ligands, and this isomerism arises when non-bridging ligands are exchanged between around the central atoms, right? Let's see an example. CO NH3 4 times OH CO Cl4 NH2. So this is a complex. So bridged complex, here OH and NH2 acts as bridges between these two central atom, that is cobalt. Okay. Now, so this is isomer with cobalt. Here these two are bridging ligands, and 4 amines and 4 chlorines are non-bridging ligands, right? Here CO NH3, so NH3 thrice Cl CO OH NH2 CO Cl3 NH3. So these two are coordination position isomers. Here one of the amine ligand, and here one of the chlorine ligand will exchange. So here non-bridging ligands are distributed among the central atoms, right? Around the central atom. So these two are complex which are having same molecular formula, but here 3 ammonia groups are attached to the cobalt. Here 3 ammonia, 1 chloride attached to the cobalt, right? So these two complexes are coordination position isomers. So these are the different types of structural isomers, right? Just for quick revision. So what is isomerism? So compounds which are having same chemical formula, same molecular formula, but they are having different physical and chemical properties due to different structural arrangements. There are two types of isomerism. One is structural isomerism, second one is stereoisomerism. In structural isomerism, there are different types of isomerisms. The first one is ionization isomerism. So ionization isomerism, compounds which are having same molecular formula, but they form in different ions in the solution. Okay, we are seeing that few examples for ionization isomerism, and they shows different physical and chemical properties. For example, taking CO NH3 thrice, CONH3 5 times SO4 Br, or taking Cl, so chlorine or bromine, CO NH3 5 times Cl SO4. So these two are ionization isomers. Okay, so these two are ionization isomers. Here in ionization isomerism, the negative ions SO4 and Cl ligands are exchanging between the ionization sphere and coordination sphere. They shows different behaviors in a solution. They form different ions in the solution. For example, when this complex is on solution which gives Cl minus and this complex solution which gives SO4 to minus. How can you identify this one? Simply by adding, for example, so basically, so the test which test are performed for chlorine AgNO3 confirmation test, treating with AgNO3, it forming AgCl white precipitate. For sulfate, we are adding BaCl to barium chloride and forming barium sulfate precipitate. For example, I am treating this complex treating with AgNO3, which gives AgCl white precipitate. Treating with BaCl2, barium chloride. So Ba2 plus reacting with sulfate which form barium sulfate precipitate actually, but here the sulfate which is present in ionization sphere, so this part will not get ionized, this part will get ionized, but this part will not get ionized, which is in the coordination sphere. Okay, so sulfate here sulfate not reacting with the barium, that means here no precipitate. Here white precipitate, we are getting white precipitate here because of Cl reacting with the Ag plus, we are getting AgCl white precipitate. So coming to this this complex, so here also reacting with AgNO3 and BaCl2. Now here reacting with AgNO3. So here Ag reacting with actually chlorine which gives AgCl precipitate, but here chlorine which is present in the ionization sphere. So it's not reacting with the Ag plus, which is not available as Cl minus. So that's why it is not reacting with the Ag plus and not forming AgCl precipitate. So here no precipitate. Here barium chloride which is reacting with the sulfate. Here sulfate which is present in ionization sphere. Here sulfate present in coordination sphere. Here sulfate present in ionization sphere. So coordination sphere will not dissociate. So here you not getting any SO4 2 minus ions. But here which is present in sulfate which is present in ionization sphere. So here you are getting sulfate SO4 2 minus ion. So which is reacting with Ba2 plus and forming barium sulfate white precipitate. Okay, right. So these are the different properties of the ionations. They have same molecular formula, same chemical formula, but they are they shows different physical and chemical properties. And the next one, hydration isomerism. And hydration isomerism, the solvent molecule exchanging with the negative ions which is present in ionization sphere. So you have seen examples, that is CrH2O 6 times Cl3, first example, and CrH2O 5 times Cl2 H2O. So just replacing one H2O with Cl, which is present in ionization sphere. So they are having three complexes. So three complexes shows the three different physical and chemical properties. The color also different. For example, if you see the first complex, that is CrH2O 6 times Cl3. So that complex having a violet color. Okay, if you see the next complex, that CrH2O 5 times Cl2 and H2O. So that complex shows light green. Okay, and next third complex, CrH2O 4 times Cl2 and ClH2O. So that complex will shows will having dark green color. Okay, so they are all these three complexes having same chemical formula, but they are having different physical and chemical properties due to different structural elements. And the linkage isomerism also. Linkage isomerism, the complex which are having linkage isomerism arises in the complex which are having amidine ligands. What are amidine ligands? They are having monoidine ligands which are having one or more donor sites like CN, SCN minus, NO2 minus, all these complexes, any complexes that are containing these type of ligands, they shows linkage isomerism. Okay, and next coordination isomerism. So in coordination isomerism, both cationic and anionic are complexes. That means we are having cationic complex and anionic complex. So both are complexes. That means we are having two coordination spheres. In between those coordination sphere, one coordination sphere is cation, which is left hand side. One coordination sphere anion, which is right hand side. Okay, and the next the coordination isomer for this complex is just here the ligands are distributed between these coordination spheres. So you are getting coordination isomers. Okay, right. Next ligand isomerism. That means the isomeric ligands. You have seen, I told you an example in the previous example, that is T and PN. Two different isomeric ligands. That is 1,2 diaminopropane and 1,3 diaminopropane. Both are having two donor sites, that is NH2 and NH2, but the position is different. In PN, the two amine groups which are present in 1,2 position, but in TN, the two amine groups present in 1,3 positions. So TN, CH2, and H2, 1,3 positions, we are putting NH2 groups, right? That means trimethylene diamine. So that's why it is called as TN. Okay, next PN 1 comma to propane, 1 comma to diamine propane, right? So when these type of ligands are associated with the complexes, they are showing ligand isomers. That means the complexes are the isomers are called ligand isomers, right? And then polymerization isomers. Actually, the polymerization isomers are not true isomers. Polymerization isomers because they are having different molecular composition. Polymerization isomers are not true isomers because they are having different molecular composition, but they have same empirical formula. They have same empirical formula. Let's say for example, if you see that example, I told you that means PTNH3 twice and Cl2, which is polymerized isomer with PTNH3 4 times, that is which is present in one coordination pair, and PTCl4, that is second coordination pair, that is cationic and anionic coordination pairs. So in both of these complexes, the first complex is having 1 platinum and the second complex is having 2 platinums, but the ratio is same. Here 1 platinum, 2 amines and 2 chlorines, that means 1:2, 2:2, and next one 2 platinums, 4 amine groups and 4 chlorines, that means 2:4, 4. So the ratio comes out to be 1:2, 2:2. That means they have same empirical formula, but they have different molecular composition, right? And the next last one, coordination position isomer. Coordination position isomers occurs in the complexes which are having bridging ligands, like here. Coordination position isomers, bridging ligands, and also having non-bridging ligands also. So here the isomers arises when the non-bridging ligands are exchanged between around these central atoms. So those isomers are called coordination position isomers, and the phenomenon is known as coordination position isomers, right? So these are the different types of structural